introduction here. Can you guys hear me okay?
Yes, yes.
Perfect. I suppose you see my my slides right in the play mode. Sometimes sharing with Zoom with multiple screens give me issue. But anyhow, it is my pleasure to present this deicing topic with this group here. It's always this was one of my favorite project, I would say, projects that I have done in the past. It was really fun, because we are attacking a very practical issue, especially in Alaska, Anchorage. We deal with ice and snow throughout the winter. And this issue is not just an Alaskan issue. Many of the, the entire northern states, right? You have from the East Coast all the way to Northwest. You have ice or snow or icing issues all over the places. It poses a very significant hazards to the traffic, pedestrians. So it is a very worthy transportation problem to study. So my topic today is going to be on the carbon fiber tape-based electrical de-icing system. I would report our study, from the laboratory testing to field testing, to some application projects, pilot testing projects, I would say. And then I'll talk about some application issues that we have observed. I'll touch a little bit on the commercialization aspects of this technology. Okay, I just click. Yes, all right. Here's going to be the outline of today's talk, as I have just stated. Many of you have had experience with de-icing. There is a spectrum of methods already been researched, from mechanical to chemical to thermal methods. I know the director of Triduo, I don't know how to spell the name of the center here. I'll try here. Xianmin has done some very significant work in the chemical aspects, trying to come up with organic compounds to melt snow or ice, by the chemical methods. But they're predominantly right now, I think the methods being applied in Alaska, those are mechanical methods here. It's basically, probably mechanical with a combination of chemical methods. Mostly, I see plowing trucks coming, after each snowstorm, with but sometimes when you have an icing event in the forecast, they would apply the de-icer on those key sections, cross sections, for example, to prevent the icing from happening, because if you have ice sticking on the surface, it's going to be very hard to remove. For the thermal methods, that's actually what this research is focused on. We could divide them into internal heating elements versus external heating elements versus electrical conductive concrete, which basically the whole overlay on the road is a conductor. For the internal heating elements, you could have ground sourced heat pipes embedded in the pavement, or hot fluids, heat pipes that is embedded, solar sourced heat pipes, electrical heating cable, like heat traces that has been used pretty extensively, and versus new materials, I would say, for example, the carbon fiber heating wire that's been reported in the past. Many of those methods, of course, no method is perfect, as you have learned. The snow and icing issue, first of all, posing safety issues. That I have talked about that, in the broad cold regions. The methods of the drawbacks, the issues that exist for the traditional de-icing method, for example, for applying salts, that's probably also pretty commonly used in the Midwest, in the northeastern part of the states. Corrosion to the rebars, damaging to the concrete, to vehicles, a common problem. The durability of pavement, when you apply salt or chemicals on the surfaces, pollution to the environment. And for some of the mechanical system, hydronic system, for example, the installation and the maintenance of those tubes, manifolds, those are very complex. I have pictures here. And some methods are just being too labor intensive or expensive. So there is a need for environment-friendly, cost-effective, yet easy to install de-icing technology. Here are some examples of the issues I have just mentioned. Oops. Yeah, I hope you can see my mouse moving on the screen here. I don't know if you guys have noticed in Anchorage, when they apply some of those de-icers, when those stuff got onto your car, it's very difficult to wash, out, to clean up. It's sticky. Okay, here is an example of a hydronic system where you basically have those glycols being heated and circulated by those tubes. Look at this valve manifold system. It's very, very complex. When something's broken, more often you don't notice until it's too much of leakage of the glycol into the ground. So the objectives of this study was to develop more advanced resistance heating de-icing or anti-icing system based on carbon fiber tape. Okay, I'll talk about that a little bit later, and then evaluate the feasibility, reliability, and the cost effectiveness of the system for pavement de-icing or anti-icing, and I will discuss some field application issues. Before we settled on carbon fiber tape, we experimented on the carbon nanofiber paper because of its superior properties pretty early on in the laboratory with my collaborators from the University of Houston. The result was very promising, but the problem was the carbon nanofiber paper. It was very expensive, and it was, the production was barely started. It's not quite available yet. Not to mention the cost. But then, we were, still looking into the potential of this technology. We did numerical simulations to try to come up with some parameters to prepare for our field testing. And then, we found out the carbon nanofiber paper was not available, essentially, when we were testing. So we then went back to the regular carbon fiber, especially the carbon fiber tape that's already woven, in a certain width. That's much easier to handle. The property of the regular carbon fiber tape is really amazing. It's highly conductive, it's durable, it's very light. I don't have to mention, of the high tensile strengths, of the carbon fiber tape that is being used for different to manufacture composite materials. For example, the Dreamliner of Boeing company, they use the carbon fiber extensively. Many of you, if you read bikes, the carbon fiber composite bikes, they're very light, very strong, very durable. So we figure, this has potential, to be used for de-icing, and also, the price of carbon fiber tape, because of the application, because of the broad application, it's becoming cheaper and cheaper. So that was the original incentive for adopting carbon fiber tape for de-icing. We essentially, trying to assemble this this panel, like this one. You have this carbon fiber tape lined up parallelly, and then you have those electrodes that are connecting them together so that you can charge it with electricity, and deliver heat to the surface, okay, of a pavement, a segment of pavement. So the first field test, it was, we constructed a 12 feet long 5-segment test sidewalk by one of our buildings on UAA campus, the University of Alaska Anchorage campus. Oh, I'm sorry, it's 30 feet long, actually, it's not 3 feet long. 48 inch or 4 foot wide. And we divide into 5 concrete blocks. We use those 2, 1, 5 as reference, but there are 2, 3, 4 as the test segment. It was actually built in September of 2010, so that's more than 10 years ago now. Here is a cross section of the sidewalk design that the carbon fiber tape, I believe, is buried. Hold on, the panel is buried right here. Okay, so there are sensors installed to thermocouples actually installed to capture the temperature data, and at the bottom we have insulation, and on the sides as well. At the base, it was non-frost susceptible material, a standard cross section for a sidewalk, for example. That the pedestrians would access in the winter time. On the top, it was 3 inches of concrete. Here is pretty clear. So the entire thickness of the concrete was 4 inches. The insulation was about 2 inches thick to preserve, the heat, to make sure it's not wasted. Here is a plan view of the distribution of the thermocouples to gather temperature data. And we do have thermocouples on the surface of the carbon fiber tape, just to measure, how high the temperature can get. We don't want the temperature to be too high to overheat the concrete. Here are a few pictures documenting the fabrication process of the carbon fiber tape de-icing panel. Those are the carbon fiber tape. Those are copper bars used as electrodes to supply energy or to energize the system. And here is a panel that's being coated before it's finalized. Here are a few pictures documenting the construction process of this test sidewalk. Here's Dr. Song, my collaborator from University of Houston, that we lay down the heating panel, and then you have the rebar cage, pouring concrete, and it's pretty much down here. Okay, within an afternoon. It was nice and quick. A little bit about the power supply and the control system. Because of the high conductivity of the carbon fiber tape, okay, and also for the safety concern, we were actually using pretty low voltage. I think we were using 36 volts of electricity to energize the heating panel. So from regular power source, we have transformers, and then we have relays to supply power for those 3 segments of 3 tester segments, with those 3 control units, and we have a data acquisition system as well as a control system, coupled together to collect the data. Here are the first batch of pictures. Before there was September, I think by mid-October we had our first snow. With a little, probably half an inch of snow. in mid-October, and of course we were really excited to see how the system works. We did not know if it was sufficient to melt the snow. So we waited until the snow is down, and then we turned on the system. So the first test was a de-icing experiment. You wait until the snow is coming, and then you turn on the system. That's 1 hour after the system was on, about 2.5 hours. It's almost gone. So 3 hours. It's almost there. The snow is melted and the surface is almost dry, actually. So that's actually presents a very nice condition for you to walk if you wish. Okay, so now how about the let me see if I can move this stuff away. Yeah, this was a couple of pictures showing the anti-icing experiments. Okay, so before I go further, de-icing, is when you have the snow on the surface and you want to melt it. Okay, but anti-icing, we meant to prevent any snow from accumulating. So basically, in anticipating a snowstorm event coming in, so you would preheat the sidewalk just in time, so that when the snow is coming down, the surface would be warm enough to melt any snow that's dropping, coming on the surface. Okay, so that was the very first experiment. Actually, it was, I forgot, it was probably January, I would say, of 2011. As you guys can see that, we had a pretty big snowstorm. This was about 2 feet of snow coming, in Anchorage. That happens not too often, but that was a particular year. Okay, the winter of 2010 to 2011 was a record-setting year. I think we had a total of 140 inches of snow. Okay, so that was a record. On average, we are talking about 75 inches of snow, but in that snowstorm alone, we had about 2 feet of snow. As you can tell, that the test segment, was snow-free, actually. So that was amazing. We were really happy. You guys noticed the camera right here. This was a view, that was November, okay, 2011. This was a shot of the night when the snow was coming down, but you see the surface was, there was no snow accumulated, while, on other places it got piled on. Okay, so that was a really interesting experiment. We were really happy, with the results of the system. Here are some data showing the temperature on the, across the test segment during the manual de-icing event, basically, melting snow after it's accumulated. The red one was on the surface of the carbon fiber tape. You can tell that the temperature went to about 12, 13 degrees Celsius, but there are other places on the surface, it was lower, about 5 degrees, between 10 and 5 degrees. In practice, we don't want to just use we don't want probably to manual control. Like, we would prefer automatic system, to give us a snow-free surface. So in the automatic control that we designed, essentially, we were controlling the temperature of the surface to be, just a few degrees above the melting point of snow. So, between 2 and 4 degrees Celsius. So the temperature would be oscillating in between. This way, it's more energy efficient, and you don't waste too much heat, by radiation, by wind, by convection. Yeah. Okay. So here are some data. As we talk about de-icing, right? Cost is always a big factor. So people wonder, how much am I going to spend on electricity, to melt the snow on my driveway? Okay, so people, we are fully, aware of this issue. So we've been tracking the numbers for each snowstorm from the winter of 2010 to the spring of 2011. And we had many snowstorms. Here are just some representative ones. The cost of melting snow, dollar per square meter per centimeter of snow. Okay, you talk about probably 15 cents to a few cents depending on the ambient temperature, the wind speed. You have many factors affecting that. For the anti-icing, essentially you have to preheat the pavement, okay, in anticipation of the snowstorm, so that you don't have any snow accumulation on the surface. So the cost here was more like, we talk about days, dollar per square meter per day, of operating. You talk about 50 cents, 80 cents, 20 cents. Depends on the temperature, the wind chill, and how much snow, of course, it was coming down. And clearly, when the temperature is higher, the cost would be lower. That you would be able to anticipate that. The wind chill, the wind speed is also a big factor. When if it's -5 degrees, but the wind is blowing like crazy, you would expect more energy being wasted by convection, so more cost, you would expect. So we used the wind chill versus the cost. Again, you see, you see a correlation there. Okay. The average cost, being about 5 cents per square feet, per square foot per day. It's always, a good idea, or people are always curious, how your system stack up with other existing systems. For example, electrical heating cable from the early 60s, hot water system, conductive concrete mixed with steel shaving or steel fiber, conductive concrete with some other, carbon particles or steel fibers, or carbon fiber heating wire, versus our system at the very bottom. Operating cost, dollar per square meter or per storm. Okay, it depends on the units. Sometimes it's harder to compare to power density, how much power you need to deliver per watt. Watts per square meter, or the unit cost. You talk about the dollar per square meter per centimeter of snow. Different parameters. Our system is better, not even if not the best, but it's definitely more. It's very efficient, and it's comparable, if not they are superior to the existing system. For example, the conductive concrete, for example, this was 74 cents per square meter per storm, but ours is about $1.50 per storm. Of course, some of the cost we have to convert, and also depends on where the test was conducted, per storm. That's also a pretty ambiguous, concept. How much snow was dumped, during the storm. It's probably not necessarily the same. But anyhow, the system, turns out, it's still affordable. I'll put it this way here. Okay. If you look at the operating cost, if you want a more specific example, for example, here I have a driveway, for example, okay, about 800 square feet. And that's pretty standard. And in Anchorage, we have many hydronic systems installed. They're using heated glycol for snow removal, snow melting. So the main cost of a hydronic system, essentially, you have a glycol boiler. It's going to cost you around $15,000 to install. You have lots of tubes to install, to buy and to install. That's about $3,000. And then, the total installation cost totals to about 20K with the unit cost of $25 per square foot. Okay, the operating cost was about $240 per month, based on the data we gathered. Now, if you would use the carbon fiber tape de-icing system, using electricity directly. So based on our small scale test, I think the cost would only drop if you consider the scale effects. The installation cost was about $1,000, so that amounts to about $14 per square foot, with labor of about $17. The operating cost was 5 cents per square foot per day. So you talk about for a driveway 800 square feet, operating cost was about $160 per month. Okay, if you assume you have 10 snow days, that's on the average for Anchorage, that's probably already a lot, compared with other areas. So $160 per month, even if you hire people to remove snow, and every time they come here, $50 at least. So 3 storms, $150 is already gone. So that is, actually pretty affordable, I would say. Now, the carbon fiber tape system, one of the advantage of the system was that because we're using carbon fiber tape, right? It's a flat surface. So the heat actually is delivered to the surface, very uniformly. So we don't have to overheat the carbon fiber tape to make sure the adjacent area is warm enough to, melt snow. So here to the right is a FLIR, a thermal image of our testing slab, that you see, the temperature is actually, much more uniform than a hydronic system where you see those tubes, right? They are circling, in the concrete, but look at those, white spot where you talk about, 10, probably 15, 20 degrees. I've been to some of them. Actually, the high temperature was about 13 degrees here. Okay, but you touch it in the winter time, it's pretty hot actually. It's very warm. So imagine, you have lots of heat being radiated or being taken away by the wind. But in our system, it was about 5 degrees Celsius, because we controlled the surface temperature to about 5 degrees Celsius. So it's more uniform. It's less. It's just enough to melt snow. So our system, system is able to deliver the energy more uniformly to the surface. I would say it's easily scalable. You just multiply your circuits, just add on segments, add on panels. The maintenance is low compared with your hydronic system using glycol. You're always concerned about the leaking of glycol, environmental concerns over there. The system, of course, because it's carbon fiber tape, is very flexible. Doesn't matter of what kind of shape you are talking about, right? It does not have to be flat. It can be a curved surface even. Okay, so it's versatile. You can apply it to other cases. Now, before you want to apply it to practical cases, people are raising questions about the issues. For example, how survivable the system is in a harsh environment. Pavement cracking, thermal cycles. You have freezing, thawing, heating, and cooling. Corrosion of rebars. Do you have any induced current? Because you are charging carbon fiber tape with voltage, right? What about the rebars? Just sitting right above. And for commercialization, of course, you have lots of regulations. One of them was the UL certification for any electric stuff. So the first issue, okay, how survivable it is, in a harsh environment, for example, pavement cracking. So we tested it with concrete slabs, pretty big concrete slabs. Here, for example, it's a 5 feet long, 1 foot wide slab with carbon fiber tape embedded, and we were conducting 4-point bending test to induce a crack in the concrete slab and see how wide or how long that our carbon fiber tape can, how wide a crack that can rupture the carbon fiber tape. This was obviously in the indoor test. I'm sorry, 3-point bending test. Okay, it's very similar. Here's the scheme actually. The black line is the carbon fiber tape. This is the concrete block. You have a hydraulic actuator trying to induce a crack right in the middle, and we're using laser sensors to measure the deflection as well as monitor the width of the crack. Here's a snapshot of the system setup, and here is the concrete slab here with the carbon fiber tape embedded to the lower half of the slab. That's the deflection monitoring system. And in the meantime, of course, we were monitoring the resistance of the carbon fiber so that we know how many fibers have, we can estimate what's the percentage of fibers that that is broken. Here are some pictures documenting the final stages. When the crack was about, I think, almost 3/4 of an inch. I think that our carbon fiber tape broke, and there was some closing, although still pretty hard to see the black carbon fiber, but the ruptured, they're broken over there. Here's the data showing the development of the deflection versus the force applied at the middle, and here's the resistance changes. Resistance, I believe. Yeah, it's right here. This is 6.08 to 6.15. Okay, the change, it's not much here. So even if you have crack initiated, the resistance change was still pretty small. There was a little drop there, but the next one is a 4-point bending test that gives us a better control, I guess, on the crack development here. Here's the force applied on top of the system. When you have the first crack, then you have a sudden drop, of course, in the force. But here is the resistance. So I think we have 2 carbon fibers, 1 and 2. The resistance was, pretty consistent, around 40 ohms, until the deflection was about 7 centimeters. The maximum crack measured about 6 millimeters in the 4-point bending test. This was the carbon fiber that's directly buried, into the concrete. So in other words, there was no coating, okay, on the surface. If we have coating, because the coating epoxy, would allow some movement, okay, between the material and the concrete. So it only would allow the carbon fiber tape to survive larger cracks. So there was, the on the structure on the cracking side, how. So we have some idea there that in the small cracks, our system would be easily, can easily survive the system, unless you have much larger cracks. But back then, if the pavement is beaten up, sometimes it's probably time to replace it now. Anyhow, how about the induced current? How is that going to affect those rebars? That was one of the concerns by bridge engineers. So, we tried to measure, but because the current, probably it was too small, and we could not measure any current, in the rebar system. We used a source meter to do that. Later on, we resorted to computer simulation to look at the induced current in the rebars. We talk about narrow amps. Okay, so that's very, very tiny. It's deemed to be less than 5 nanoamps and not significant to be of concern to the induced current and the corrosion for the rebars. The system. This slide was prepared a few years ago now, but this test slab has already been demolished. I think it's before the COVID because of the construction. But I will have another example that was a pilot testing system. But anyway, for the test slab, we experimented. We observed for 3 years with a system turned on for every winter, and we did not observe any cracking on the surface. There was no disintegration of the slab integrated, even when we were demolishing it. The system, the carbon fiber and the system was still in good contact. The electrical properties of the heating panel, we also, we monitored, and it was very stable because it's embedded in concrete. I guess, it's not in contact with oxygen, with air. So corrosion of copper was also of not, insignificant concern. This system, I would say, first of all, it's based on commercially available carbon fiber material, and the cost of material is also dropping pretty significantly. Okay, so this application potential there. System, of course, can be powered by electricity, either it's from the grid or renewable sources. Especially for remote areas. If you talk about a bridge, you could have a wind turbine installed, or even solar system installed to power the system. Cost, is I would say is affordable based on our comparison with the existing hydraulic system. The potential applications, is pretty broad. Private driveway, for example, I talked about. Street crossings, that's where most of the traffic, accidents occur, especially, my experience with Anchorage. When you see a red light, you're trying to stop, but everybody was trying to stop, so the surface was already very slick. It's very difficult. Bridge decks, when the bridge decks are crossing waters, for example, especially when you have moisture, it's very easy to form black ice, very dangerous. It's hard to see by drivers. Sidewalks, that's also very important because it's used heavily by pedestrians. Schools, hospitals, department stores in an urban environment. This would have a lot of applications. I would touch, on the commercialization aspects. We do have 2 patents granted by USPTO. And I'll talk about our first application was on our UAA campus, folks in the maintenance department are really interested in the system because, snow can come down anytime, and the Russian people are there to clean up the snow, put on pea gravels to make sure no students is going to fall on their property, because that's a big liability. So I'll talk about the application, and I will touch a little bit on the commercialization UL certification aspects. So this was a UAA building. They do have lots of traffic here. So And this sidewalk was already beaten up, so they decided to remove it and experiment with our technology. So the construction was a little late. Excuse me here. It was in November, so once they dug out the system, but then the temperature dropped, so they had to make sure the fill material was not frozen. It's not going to be found. And this is the insulation put at the base, at the bottom. And then we poured in, you guys noticed probably the tent was already set up, because for the concrete to cure, you need a temperature higher than the freezing point. So they set up a tent and blowing hot air into the tent to install the system. Here is our carbon fiber heating panels that's being laid up on wet concrete. The folks from the utilities, from this is our former chancellor, they were pretty excited about this thing. They were talking about having this installed in the driveway, actually, when we were doing this. Rebar's been laid up on the top, and some more pictures showing, here is we are pouring the cover concrete. System is almost ready. You have power supplies, you have sensors to collect data. It's all from a site ditch. So here is the control panel. Here's the system ready, and not too long after, we had a freezing rain, coming down. That's the worst you can have in the winter. And it's basically coating the surface with a layer of ice. I think it's about a half an inch thick. It's very dangerous, very treacherous. It's hard to remove even. But this system worked beautifully, I would say. The system, there was no, you can see it's already, it's gone. There was no ice on this system. Here's the sensor detecting ice. I did not mention much about that here. And on other places, you can see those shiny ice, but this one was just nice and clean. Now, another event was when it was really, really cold. We had about 18 inches of dry snow. Okay, the temperature was probably like -15, -20 C. Okay, really cold. So system kept up really, really well. That's when you test the limit of your system. Cold, you have to reach the temperature, mix the system, works the system, and then test the limit of the system, essentially. This was just some drifted snow, but otherwise, it's pretty clear. It's dry, it's easily, it's nice to walk. This was just drift, fluffy snow on the top. So this was the dry snow of about 18 inches. Now, not to, we have the spectrum of stuff coming in. This is the wet snow event of about 7 inches in another occasion that this was my graduate student back then. Close, just a little below the freezing point, probably -2, 3 degrees. Snow was really wet. And the system has no problem to keep it up, at all. So you close in here, it's nice and clean, it's dry, essentially. Okay, that's the big difference between electric system versus a chemical system. You don't have any residual water on the surface. So that was the pilot testing. I can report this system is still here. Okay, it has been about 10 years now. It was 2012, I would say. System is working beautifully. That we don't see any deterioration in the performance, in the resistance, and there was no cracks, at all. In the system. The university is actually pretty happy. At one point, the they were renovating the system. They were talking about they had to remove the system, but somebody from the maintenance department stopped them. They really want to keep this one to see how long term it performs. We had some investors coming in to invest in the system, and we actually started a commercialization process. The big hurdle, I have to, that was, I can talk about that for a long time. It's a long story there. Commercialization is not easy, but the hurdle we stuck right now, I would, or we're trying to fix, jump over was the UL certification. They have a very harsh testing protocols for the system. Essentially, they want to submerge the whole system in water and to make sure there's no leakage of anything, even though the system could be working on a very low voltage system, 36 volts, for example, but they have not seen because this is a newer system. I guess the testing protocols was more for the high voltage system, but they're sticking to that. So that's what we're facing right now. But with that, I'd like to acknowledge the sponsors of the system. It was sponsored by the Alaska University Transportation Center, by UAA, and by the Alaska Department of Transportation. I have collaborators from University of Houston. A few graduate students worked on this one, and that was, definitely a fun project, and I certainly hope someday this technology can be applied in the communities. With that, I'll conclude my presentation, and I would be happy to answer your questions.
Thank you, Professor Yang. I think we have a question typed in the chat box from what had Nasser. He's asking, would the system work in asphalt concrete paved roads?
Good question. We have not tested it in asphalt concrete there yet, but I suppose it can. I mean, there's nothing stopping it from applying the system to asphalt concrete. As you have seen, the temperature, the surface temperature of the carbon fiber tape was just a few degrees, less than 10 degrees, about 50 Fahrenheit, I think. So it's not a very high temperature at all. The surface of asphalt can go to probably 100 degrees Fahrenheit, and even higher than that in many warmer places. All it depends on the system. Basically, is looking at the thermal conductivity, right, of the surface overlay. I mean, I suppose the asphalt concrete, the thermal conductivity is not that different. I mean, if it is, you could probably add some material to modify it, to make it comparable. And I think there is advantage even, for asphalt system, because for concrete, for Portland cement concrete, it is potential for cracking, right? There is a big concern, but asphalt concrete is quite flexible. It's less prone to cracking there, unless you have some settlement issue there. That's a different story. Yeah, I think definitely it could be applied to asphalt system.
Okay, we got the second question from Tam. He asked, does temperature increase if we increase the input voltage? Can you recommend the optimum input voltage? Thank you.
Well, definitely you can. Temperature increase is directly related to how much power you input, right, to the system. So you definitely could increase the temperature if you increase the voltage. because you increase the voltage, you increase the current too. So you could do that. I see the chat here. Can you recommend the optimum input voltage? That's a good question there. I don't think there is an optimum input voltage. For us, we were also, besides the 36 watts, because that's where it's deemed as low voltage, but in less than 36 volts is low, above that is high. So we were shooting for the low voltage. We were trying to bypass the regulations, because 36 volts is deemed safe. You can touch it essentially. It's not going to kill you. It's not going to give you any shock either. But even if later on we experimented with the 120 or 240 volts from the commercial grade. That is another idea. High voltage, you are going to have lower current in your supply. Cable. Okay, so it's easier, it's less expensive, I guess, to supply the system here. But depends on what system you want to go after. Maybe it's of course, if you use a low voltage system, then you have to use a transformer. That's another layer of cost and the complexity. Okay, so it all depends on your application. I don't think I can give you an optimum input voltage here.
Okay, our next question from Douglas is, was there ever a situation where temperature could not be maintained due to weather conditions, resulting in melted snow to refreeze?
That's a good question too. Again, that has to do with that. We have not seen that because we designed our system to pretty high power density. Okay, there's a concept called power density. How much power you can input per area. Okay, we were designing the system to about 300 watts per square foot. Okay, that's in Anchorage. Temperature could be pretty low. Wind could be blowing. So we consider that. But if it's in Pavement, for example, in Washington, I don't think you guys will experience negative 25 C, right? The wind, I don't think it's going to be as as strong as here. So the power density could be lower. That there is going to vary by regions. So if you design your power density to an appropriate level, then you could avoid that. For example, in Minnesota, that Minneapolis, that could be pretty cold and pretty windy. Okay, so I would probably design it a little higher even than Anchorage, to make sure it's not going to refreeze. But the good news about this system is because when the snow was melting, it's also evaporating. So at the end, most often the surface is already dry, so your surface is not even prone to refreeze. Okay, in this case.
Okay, our last question is from Dr. Xin Shu, and he said, very intriguing talk. Thank you, Professor Yang. Do you think this system, if implemented in asphalt pavement, could help reduce thermal cracking risk of the asphalt concrete and facilitate its self-healing?
See, that's an interesting question, Xiaomi. I think you definitely have the potential. If it's really, really cold, right? For example, you're concerned about the thermal cracking, then you could input certain amount of energy to maintain a minimum temperature. So I think definitely it is possible. And also, if you want to implement a self-healing mechanism for the if you want to incorporate that in your de-icing design, you're talking about a multi-function system here now. Then you could because I suppose you need a certain temperature, right, to soften the asphalt. So you need to carefully design the power density so that you could deliver the temperature in case you want to heal it. So yeah, that's a very interesting proposal there. I would say, you know, there's definitely potential. I have seen people talking about using electrically heated system to prevent frost heaving in winter roads. Basically, you know, the same idea, right? You know, when you have cold temperature, when you have a potential for frost penetration, you just energize the system to stop the penetration of frost into your frost susceptible layer. You know, so I think it's a very similar idea, but I think here we'll talk about a more, you know, I think smart, you know, asphalt paving, you know, with functions like de-icing, prevention of thermal cracks, or even self-healing. Yeah, I think there's potential. The nice thing about this system is that it's a layer that you can locate in a certain depth to prevent, you know, basically to reuse it essentially. You know, that's the benefits of the system. If you do have small cracks, the system is able to survive. Okay. Otherwise, you know, if you have a conductive layer overlay, but if you have a crack there, then your whole system is probably broken, you know, the circuit. Okay, so that's a nice thing about this system is it's concentrated, but it's protected. You know, so you could design it so that so that it can survive certain conditions.
Okay, I think we got one last question from Huaja again. Yes, but then would it produce agent as is determined in rolling thin film oven test?
I don't. Are you talking about the agent of the carbon fiber, the system itself, or the agent of the pavement?
I think it's on the asphalt pavement.
Of the asphalt pavement. Okay, that's a good question here. We have seen actually, you know, that was a question about the that we thought about for concrete, for Portland cement concrete. There were some studies from the last century, 1950s, 60s, when people were building nuclear power plant. You know, you have those concrete shell subjected to high temperature cycling, right? You know, that was higher, probably 60, 70 degrees C. Even that, I think the conclusion was the aging or the damage, the effects on Portland cement concrete was pretty small, okay, if the temperature was not too high. But here, you know, our temperature was less than 10 degrees C. So because, you know, because the system can deliver heat pretty uniformly to the surface. Otherwise, if you use a metal wire, then, you know, because the gap between the wires is wider, so that, you know, you have to make sure the wires are much warmer to make sure, you know, it can heat up the adjacent concrete, right? You know, that can easily go to probably, you know, on the surface it was like 15 degrees C, but in our case the surface was just a few degrees, you know, above the freezing point. The surface of the carbon fiber tape was less than 10 degrees C. So I think, you know, it's minimal in terms of aging, you know, of the pavement.